purpose of this simple presentation is to give you guys the notes we had in class, just so that you can see about making scientific measurements and how we do it and the proper ways that we do it. Before we can do that, we have to get a few terms out of the way so that we all are on the same page with that. The first term we have to discuss is precision. And what it means for precision is to get the same results repeatedly, reproducibility, do it over and over and over. You throw the darts 10 times and you hit the same spot on the dartboard every time. That is precision. It doesn't matter whether it's the right answer or not, just that you hit the same spot every time. Accuracy, on the other hand, is how close we are to the truth or to that real answer, or on a dartboard, how close we are to the bullseye. That's accuracy. And so they're kind of not one and the same thing, and they're kind of mutually exclusive. You can be precise without being accurate. You can be accurate without being precise. It depends on the target that you're trying to hit. And what calibration does for me then is move answers that are precise close together but not close to the truth. It allows me to move them closer to the truth. It won't affect precision. Precision is based on the instrument we're using and goes back to how, if we're looking at like a graduated cylinder, how cut up the graduated cylinder is, how many lines are on it, so that how much am I guessing. Precision is going to have a great deal to do with that. But a calibration can take precise, inaccurate data and make it precise, accurate data. Something else we need to say about scientific measurements. We need to know that scientific measurements have magnitude. That means they have some number associated with them. They also have dimension, which means they have a unit, and they also are going to have precision limits. That's going to be based on, again, the instrument that we use to measure them. So in order to convey this precision limit, we have to discuss something called significant figures. And what significant figures is things that are scientifically meaningful. And so really it's an estimation of propagation of error. But in practice, if you're taking a measurement in the lab, it means every number that you can tell from your measurement device with certainty plus one estimated value beyond. So for example, if we're looking at this ruler, we're going to start taking our measurement of the white block at the number 1. I started at 1 simply to drive home the point to you that if you look down this edge, the ruler does not end right on 0. There's some of the wood sticking out. You can see some brown space beyond that. In some rulers it's more than others. So in order to be accurate, we either have to start on the 0 or start on the 1 or the 2 or whatever and measure the difference between two things. So we're going to start on 1 and we're going to call it 1.00. We're calling it 1.00 because the ruler is marked such that I can tell whether it's 1 or 1.1. So I know this place and this place for sure. And then we're guessing that it's right on the line. So we're guessing that this is right at 1.00, not at 1.01. It's not moving away from that line. On the other side, we can see that we're at 7 and 0.1 for sure. So those are our two known values, and then it ever so slightly passes the line. So I'm going to estimate that it's about one space past the line. So we know 7.1 for sure, and we're estimating we're 1/10 of the way to the next line. And so for our measurement, we take the difference between these two. 7.11 minus 1 is 6.11 centimeters, and that would be the proper way to take a measurement with a ruler. Again, it's okay to start at 0 as long as you recognize not to start at the end of the ruler. Make sure you start at 0 and then you won't have any subtraction to do. This is another type of measurement device that you see commonly in the lab. This is a graduated cylinder. It looks like it goes 6 here, then 7, then 8. So there are 0.2 marks in between each one. So I'll be guessing somewhere between 6.0 and 6.2, somewhere in between there. So when we read a graduated cylinder, we have to read this thing called a meniscus. A meniscus is kind of an inverted watch cover or watch glass, and it's caused by adhesion and cohesion. It causes the water to dip as we cross the graduated cylinder, and the thinner the tube is, the more pronounced the meniscus is. You can see it better. Really wide tubing would not have a good meniscus for reading things. We always read that meniscus at the bottom, and in this case we're going to notice that is at least 6.2, 0.4, 6.6, but not all the way to 6.8. So it's somewhere in between those two. And that's where we read it. And I'm going to estimate that that reading would be about 6.62 or 6.63, something like that. Two other commonly used pieces of lab equipment. This is a balance that we use on a benchtop balance. This is an analytical balance. What I really want you guys to see here is how many significant figures they have. Instruments like this that give you a number are already telling you everything they know, plus an estimate. In fact, if you watch them in the lab, you will see as you're doing the experiments that the last number, or maybe the last couple if it's really close to an ending like this, tend to fluctuate a little bit. But those are all that's known and an answer. So those are 4 significant figures. The balance is giving those to me. On the other hand, over here, where it says 184.7996, this one is reporting to me 7 significant figures. So the answer from the analytical balance has a lot more scientific meaning than the answer from the benchtop balance, just to make you aware of how we handle those things from laboratory devices. We have rules for determining whether digits are significant. You can read these in your textbook. I'll try to briefly summarize them here. Essentially, every digit that's not a 0 is significant. That's rule number 1. Rule number 2 says that every 0 that appears between digits that are not 0 is significant. So if I have 101, for example, I need that 0 to convey the meaning of 101, so it's significant. Number 3 says that anytime I have leading zeros, like I have a really small number, 0.003 for example, until I get to the first non-zero number, none of those zeros count. That's what rule number 3 says. A good test for this is to write them in scientific notation. If I can write them in scientific notation without those zeros, then they're not significant. Step number 4 says that if I add zeros after a decimal place, for example, I take 43 and make it 43.00, it's saying that those zeros are added on purpose, and they're indicating how far I knew for sure on my measurement device before I estimated. As such, they're part of the known and the estimate, so they are significant. Adding the zeros after a decimal makes them significant. Rule number 5 says that if I have zeros that are occurring after a true number before a decimal, they may or may not be significant. We really don't know. A number like 300, for example, could be 300 and be all 3 significant numbers, or really maybe I'm guessing that it's 300 and the last 0 is holding place, or maybe the last 2 zeros are holding place. In order to take care of this, what we do is we definitely write these types of numbers in scientific notation. If we do so, we can indicate how many of those zeros we want to count. We can write 3 times 10 to the 2, or 3.0 times 10 to the 2, or 3.00 times 10 to the 2. And each one of those would have one successively higher significant figure. So we indicate it by writing in scientific notation. And then last but not least, number 6 says that there are times when we can have unlimited significant figures. These apply when we're counting things that can't be subdivided, like persons, or maybe we're counting cars or something like that. Anytime I'm counting specific things that can't be broken down into smaller pieces, that's unlimited significant figures. This would be like 24 cans in a case of Dr. Pepper. I'm not going to take half of a can, so that's an infinite number. And the last one of those is definitions. When I say there are 60 minutes in an hour, for example, there are exactly 60 minutes in an hour, so that has unlimited zeros after the decimal, and so it has infinite significant figures and will not impact any counting of them. So we said all this to get us used to working with them, because that's what we really are going to do, especially with lab data. We're going to take measurements, use them to calculate things, and we don't want to overestimate how well we know these answers. So in order to do that, we have to know the rules for working with these significant figures. And as such, when we add and subtract, like we did with the ruler and the white block earlier, our answer will always match the least precise measurement. This means that if I have a lower number of decimal places, or whatever we're dealing with, the least precise one, once I guess on that, anything I add to that doesn't really matter. It's been added to a guess, so we'll stop with the least precise. An example of this is to take 12.03 and add it to 14.221. If we look at the 12.03, we guessed in the hundredths place. So if I take the measurement 14.221, which knows the hundredths place for sure and guesses in the thousandths, I can't keep that thousandths measurement, because once I guessed on .03, anything beyond that is a guess. So we lop it off to the least precise measurement, which means we only report back 26.25. We round off and leave off the ending. And just to remind you, when numbers are followed by something less than 5, we keep them the same. If they're followed by something greater than 5, we round them up. I know there's a little bit more precise way to do that, alternating odds and evens, but for this class we're going to leave it alone with that. If they're followed by a number greater than 5 or greater, round them up. If they're followed by a number less than 5, leave them alone. When we multiply and divide, we get a slightly different way of handling it. Instead of looking at the least precise, we go to the least number of significant figures. This is just, again, estimating propagation of error. And it's this way because when I multiply numbers or divide them, I compound the error. When we're adding and subtracting, we're still working within the same realm. But when we multiply and divide, it just makes things, blows them up. And so an example of this, if I take 88.251, that value has 5 significant figures, and multiply it by 13, that value only has 2 significant figures. My answer will only be allowed to have 2. So instead of reporting back a huge number that's like 100 blah and 10 blah 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 blah, I'm only allowed to have 2 significant figures. So I have to round that number off to 110. I don't want to write 110 because that leaves that ambiguous 0 that we talked about in significant figure rule number 5. So in order to indicate I only have 2 significant figures, I use scientific notation and write that as 1.1 times 10 to the third. I'm sorry, we would be talking about 1100, not 110. So we're going to write that as 1.1 times 10 to the third and leave those 2 unneeded zeros off. Okay, we'll skip the activity. That was something that was done in class. And we want to answer each of the following problems using the proper significant figures. So I'm going to add and subtract some numbers. So without even doing the math, I ought to be able to tell where I'm going to stop, where I'm going to round. This number, 32.2224, goes out to the thousandths place. 12.45 goes to the hundredths, and 15.2 only goes to the tenths. Since 15.2 is the least precise, that's where we stop. Our answer will have 1 decimal place, and it happens to be negative 4.6 grams. The next set is a multiplication and division, where we're going to have 4 significant figures for 17.82, 4 significant figures for 987.6, and then 2 significant figures for 12. So my answer will be only allowed 2 significant figures, so I report it back in scientific notation as 1.5 times 10 to the third. When we get to part C here, we have to be worried about order of operations. I'm going to do some things in different orders and then try to decide how many significant figures come out of my answer. If we look at this here, subtracting 19.36 minus 32.2 is going to leave me with a number with 1 decimal place. And then I'm going to divide that by 14, multiply by 2, subtract 13.636. And in doing all that, I'll track the significant figures allowed at each step. Applying to my final answer, I'll find out that I'm only allowed to have whole numbers, because the result of this part of the equation will be a whole number. So when I subtract something from that whole number, my precision is set. I can't be any more precise than a whole number. And so I'll report back the nearest whole number, which is negative 15. Then part D, it says explain how something can be precise but not accurate. If we'll remember, precise just means close together. I can have data that's consistently wrong. If you've ever been to the bowling alley and thrown your ball and always hit the gutter in the same spot before you get to the pins, you're throwing in the same place every time. You're consistent, you're precise, but you're consistently wrong, so you're not accurate. Same thing with darts. If you throw for the bullseye every time and hit the bottom edge of the dartboard in the same spot, you're consistently off, so you can be precise without being accurate. And that is lesson number 1 in a nutshell.